ascending pathways. We'd started on ascending pathways last time. We'd gotten as far as carrying the information about proprioception and fine, or sometimes known as discriminative touch, into the central nervous system, and then carrying that information from the primary sensory afferent to the second order neuron, which always crosses the midline, to the third order neuron in the thalamus, up to the motor cortex. We're going to review that pattern again today, and we're going to talk about the pattern of the ascending sensory neurons in the dorsal column medial lemniscus. The dorsal column includes the extensions of the primary sensory afferent. The medial lemniscus contains the processes of the second order neurons. And they are now, the second order neurons are going to be the ones that cross over the midline. Turns out in the DCML or PCML, the second order neurons have their processes in the medial lemniscus. Now, these neurons are carrying information. This pathway is carrying information to the somatosensory cortex about proprioception and fine, sometimes known as discriminative touch. But we have other sensory modalities in terms of somatosensation that are being carried in a slightly different pathway, but arriving at the same place. The other modalities that are being carried will be pain, temperature, and pressure. Pain, temperature, and pressure find their way through the ascending pathways in something known as the spinothalamic tract. Now, I want you to know this term because it's a kind of language that we use in neuroanatomy all the time. When you see spinothalamic, it tells you this first syllable, spino, tells you that the neuronal cell body is found in the spinal cord. Thalamic tells you that's the output region. So it tells you there's going to be a tract of conductal regions that extend from the input region of the neuron in the spinal cord to the output region in the thalamus. And we'll see this pattern in nomenclature occurring over and over again. Then I want to talk a little bit about Brown-Séquard. And the reason I bring up Brown-Séquard is a hemisection of the spinal cord. We cut the spinal cord just to the midline. And the reason I want to walk you through this is that if you understand what happens in Brown-Séquard syndrome, and you understand what information is blocked and what information still gets through, then you understand the distinction between the ascending sensory tracts carrying information about pain, temperature, and pressure in the spinothalamic tract, and the pathway carrying information about proprioception and fine touch and the dorsal column system. We'll walk through Brown-Séquard. I think it gives a much better insight into how this is working if you can see why you lose some modalities and not others in Brown-Séquard syndrome. Then what we'll do is we'll take this information all the way up to the brain, all the way up to the cerebrum, all the way up to the somatosensory cortex. As we talk about the cerebrum, recognize the cerebrum is a substantial part of the brain. And when you look at a brain, when you look at an image of the brain, normally what you're looking at is the cerebrum. But most of that cerebrum is composed of axons, composed of white matter. Only a very small amount of the cerebrum is composed of this thin veneer of 6 neuronal cell bodies. But that thin veneer of 6 neuronal cell bodies called the gray matter is where all of the synaptic activity occurs. So it's important to recognize when you talk about the cerebrum that it's only the very thin outer regions, no more than a couple of millimeters thick. That's where all the synaptic activity, where all the integration is occurring. Then all of the axons coming from those 6 neuronal cell body layers are now distributed to all parts of the brain, and they're distributed to all parts of the brain by conductal processes in the white matter. Then once we've come through the concepts of the somatosensory system and the sensory information that is coming into the region of the brain called the postcentral gyrus. The postcentral gyrus is a portion of the cerebrum that is somatosensory. But we're going to see that just behind that, on the other side of this central sulcus, this great fissure, there's now going to be a precentral gyrus, which is then motor. So when you look at this, postcentral gyrus is sensory and motor is precentral, and we'll walk our way through that. Then what we're going to do is we're going to map the body plan of both the sensory and motor cortices. And we're going to see that for each of these cortical regions, the body plan is mapped out in the neurons in those cortices. And this all started about, the understanding this started, probably 70 years ago, when there was a surgeon who literally was poking away at people's brains and asking what they felt and what would happen. And from that, there was now an understanding of the body plan's map on the surface of these regions of the brain. We'll run our way through the somatosensory system, and then we'll move on to the motor system. We really don't have time to talk about the really elegant systems in the parietal cortex, where in the parietal cortex we bring together all the sensory information. We just don't have time to do that. But once that information is brought together, then a decision is made, and we use the motor systems to affect a response. We're back to the 3-box model: sensory in, analysis, motor out, and this is going to be part of the motor out. The motor out story here is going to be that there will be an upper motor neuron that's found, whose cell body and input region is found in the motor cortex. That neuron sends a process from the motor cortex down through an area called the internal capsule. The internal capsule is a bundle of myelinated axons. If you take another course, you'll find the internal capsule contains both sensory and motor axons. Here we're only emphasizing the motor. The descending pathway now going from the motor cortex, the axons or conductor regions in the internal capsule, then crossing over the midline in a region called the decussation of the pyramids. So just as the sensory information crossed over on the way up, the motor information also crosses over on the way down and crosses over at the decussation of the pyramids. We're going to label this tract, once it enters the spinal cord, as the corticospinal tract. There's again meaning in that term. Cortico tells you that the neuronal cell bodies are located in the cortex, and the spinal part tells you that its output region will be in the spinal cord. Specifically, we're going to find that the output regions for this corticospinal tract will be in the gray matter of the ventral horn gray matter. And those upper motor neurons now will synapse directly onto lower motor neurons. Then there'll be a monosynaptic pathway from the upper motor neuron to the lower motor neuron, and that lower motor neuron then is going to go out from the central nervous system, as we've seen in the reflex arc. It's going to go out from the central nervous system and join a spinal nerve. And from the spinal nerve, that is then going to innervate muscle. There's a term here that I want you to know, and we probably won't come to it until Monday. But the term we want to talk about is something known as the motor unit. The motor unit has a definition. The motor unit is defined as the lower motor neuron. If you put your phone away to appreciate it. Yes, you. Put your phone away, please. Thank you. So, the motor unit is defined as the lower motor neuron and the muscle fibers that it innervates. And each lower motor neuron will innervate several muscle fibers. In some large motor units, it may be as many as several hundred muscle fibers. In small motor units, maybe no more than 10 or 20 muscle fibers. So each motor neuron innervates multiple muscle fibers, but each muscle fiber receives input from only one lower motor neuron. It's an important concept. When the lower motor neuron fires, then multiple muscle fibers will simultaneously contract. And they will simultaneously contract because at the neuromuscular synapse, we have a classical synaptic response. At the neuromuscular synapse, the lower motor neuron releases the neurotransmitter acetylcholine. And those receptors that Langley talked about, this acetylcholine will bind to the nicotinic acetylcholine receptors. The binding of the acetylcholine to the nicotinic acetylcholine receptors causes those channels to open. Sodium comes in and depolarizes the muscle fiber membrane. The muscle fiber membrane then, once depolarized, can activate or turn on voltage-gated sodium channels, and we see the same pattern played out again, where the action potential propagates along the membrane and causes muscle contraction. That story we'll have to leave till Monday. But what I want to do here is begin with a discussion of ascending sensory paths. And let's first recapitulate what we had last time, where with our ice cream cone diagram, we had the spinal cord. Let me make this a little bigger so I have some more room. We start with the ice cream cone diagram with the cone down here. And then above that was the brainstem. And beyond that was the diencephalon, which included the thalamus. And above the thalamus, we drew in these sort of blue ovals, and we labeled these blue ovals as the cerebrum, but more specifically, the cerebral cortex. And more specifically than that, the so-called somatosensory cortex. Where we began was the crude leg. It's a terrible ankle. And we started with the quadriceps muscle. And the initiation of that discussion was to talk about the neurons, the stretch-activated neurons. The input region of these stretch-activated neurons was embedded in the muscle itself, but these were primary sensory afferents whose cell bodies were located in the dorsal or posterior root ganglion. We followed through last time how the neuronal cell body would also have an extension of the neuron into the central nervous system. And the reflex arc, let's draw the cross-section over here. The reflex arc was such that the primary sensory afferent carrying information from the stretch receptors about proprioception, that primary sensory afferent, this neuronal cell body here sent a process in, went all the way down into the ventral horn, where it synapsed directly as part of the reflex arc onto a lower motor neuron. This neuron now also has a branch, a process that extends into this part of the cord. We'll divide it into the left and right sides. And we labeled this part of the cord the dorsal columns. And I'll remind you the dorsal columns are part of the white matter. So that's the view in cross-section. Now let's follow the process of this neuron, this primary sensory afferent. The primary sensory afferent, once it enters the dorsal column system, then extends up the cord. This is the process of a single neuron whose cell body lies in the dorsal root ganglion, extends from your thigh into the dorsal column system, all the way up to this region of the brain, which we labeled last time as the brainstem. The output regions of this blue primary sensory afferent are found in a particular region of the brainstem known as the dorsal column nucleus. So again, the term nucleus, there's meaning in that verbiage. Nucleus is a cluster of neuronal cell bodies, a cluster of input regions in the central nervous system. The input regions that we're talking about here are for these orange neurons. These orange neurons are the second order neurons. Now, while the neuronal cell bodies are found here in the dorsal column nuclei, this second order neuron sends out a process, crosses over the midline in the brainstem and a region known as the medial lemniscus. That's where the ML part comes from. And then crosses over in the medial lemniscus, and then ascends the cord a short distance into a region of the thalamus, known here as the thalamic. Let me give myself a little more room. Into a region known as the thalamic relay nucleus. Then this third order neuron here in red sends a process up to the somatosensory cortex. So this third order neuron extends a conductal region to the somatosensory cortex. The somatosensory cortex, located on the postcentral gyrus. Now, I should say it's the postcentral gyrus of the cerebrum. But let's back off a little bit and recognize what we've done. We have a primary sensory afferent whose neuronal cell body is in the dorsal root ganglion. Sends a process into the central nervous system, ascends the cord as far as the dorsal column nuclei, where the primary sensory afferent synapses onto the second order neuron. This orange second order neuron crosses the midline. So let me put in a dotted purple line here. That's the midline. We're bilaterally symmetrical. What we see on the right, we see in mirror image on the left. Well, let's now do the same thing over here on the left leg. The quadriceps muscle. The primary sensory afferent, having its neuronal cell body here in the dorsal root ganglion. If we were to go to the other side, we'd see again, we have this primary sensory afferent sending a process into the dorsal horn, all the way down to the ventral horn, but then again, forming a branch that enters the dorsal column system. So again, here's the neuronal cell body, comes into the cord, ascends the cord all the way here to the brainstem. In the brainstem, it forms a synapse. It forms a synapse onto a second order neuron. The second order neuron crosses over the midline and ascends on the opposite side to the thalamic relay nucleus. In the thalamic relay nucleus, the second order neuron synapses onto a third order neuron, and the third order neuron sends a process to the somatosensory cortex. So those systems are precisely bilaterally symmetrical. And this system, which we gave the name to of the dorsal, let me put it in the upper panel. The name that we gave to that tract was the dorsal, more properly the posterior, medial lemniscus. The dorsal column medial lemniscus pathway, I should say column. The dorsal column medial lemniscus pathway carries information about proprioception and discriminative touch. This somatosensory pathway we take for granted. We just use it all the time and we just assume it's going to be there. And it's a remarkable system. And the example I like to use is one a situation we've all found ourselves in. You come home late at night and it's dark and you're about ready to go into your house. And you realize that you've made this mistake of not getting your keys out. That your keys remain someplace in your backpack. You couldn't even remember where in your backpack. They're buried someplace. So you open up your backpack and you start fishing through your backpack. And you can feel around without opening your eyes. You can feel around in your backpack and you'll find your keys. So you say, oh, and we know this. We reach in, you find the keys, pull it out. And then you say, well, I've got a whole bunch of keys here on my key ring. But what I need is the house key. So you start feeling through each of the individual keys. And you'll find your car key. You'll find the key to your bicycle lock. You'll find the key to your locker at the gym. And they say, oh, here it is. It's the house key. And you feel that house key, and then you feel around with your other hand, and you find the lock. And you know in space where your left hand is, you know in space where your right hand is, and you put that key in the lock, turn the tumblers, and walk in without having seen anything. You know where you are in space, and you have the fine touch to distinguish one key from another. It's an astonishing system, and we use it all the time. It's the one where you can close your eyes, take your hand, and touch your nose. That's how you know you are in space. Where your hand is in space, that's proprioception. And then there's fine touch. And that's all this DCML pathway. But there's another set of modalities that we're going to see is carried in a region called the spinothalamic tract. Again, let's unpack this word. If we unpack the word, it tells us spino, it means the cell bodies. Or the cell bodies or input regions are located in the spinal cord. But then it also tells us that the output regions are in the thalamus. So now let's follow this path. Oh, I should say one more thing. Spinothalamic tract carries information about pain and temperature and pressure. So now let's follow one of these pathways. Let's now imagine down here in our right toe, we have a pain neuron. This is going to be a primary sensory afferent. So we follow its process. We'll find, because it's a primary sensory afferent, its neuronal cell body is found here in the dorsal root ganglia. All primary sensory afferents have their cell body in the dorsal root ganglia. So this is the cell body of this primary sensory afferent. It then extends a process into the central nervous system. So let's now take this neuron with its cell body in the dorsal root ganglion and just simply label as a pain neuron. It could just as easily be a temperature-sensitive neuron or a pressure-sensitive neuron, but it's a primary sensory afferent. It has this great long process that goes into the periphery and the spinal nerves, but then it has a process that comes into the central nervous system. The primary sensory afferent has its ending almost immediately here in the dorsal horn. So its output region here is in the dorsal horn. And in the dorsal horn, this primary sensory afferent synapses on to a second-order neuron. Remember the rule. Second-order neuron always crosses the midline. This second-order neuron wends its way across the spinal cord and enters a region down here known as the spinothalamic tract. So if we now take this image of a cross-section and superimpose that image onto our longitudinal view, this primary sensory afferent, as we've shown here, synapses onto a second-order neuron, right here. Crosses over the midline. This is part of the spinothalamic tract. So here's the neuronal cell body, it's its input region, crosses over to the other side, because all good second-order neurons cross over to the other side, ascends the cord, goes buzzing right by the dorsal column nuclei, and finds its way here to the thalamus. And in the thalamus, this second-order neuron synapses onto a third-order neuron, and the third-order neuron now sends a process to the postcentral gyrus, to the somatosensory cortex. We can do the same thing on the other side. We can now, from the left leg, imagine a pain neuron down in our toe. Processing comes in, has a neuronal cell body in the dorsal ganglion, sends a process into the cord, synapses on to the second-order neuron, second-order neuron crosses to the other side, enters the spinothalamic tract, and ascends the cord on the opposite side all the way to the thalamic relay nucleus, and then in the thalamic relay nucleus, the second-order neuron synapses onto a third-order neuron that now sends a process to the somatosensory cortex. So we've now drawn two pathways, which are bilaterally symmetrical. One pathway carrying information about proprioception and fine touch, and the other carrying information about pain, temperature, and crude touch. Now the next thing what I want to do here is I want to take an imaginary scenario where we're going to cut the cord, but we're only going to cut the cord to the midline and ask what gets through and what doesn't. Yes?
So that primary sensory afferent neuron has to be, if it's in your toe, it has to be 3 foot long.
So the statement here is, if this is a primary sensory afferent with its input region in your toe, it must be 3 feet long. Yeah. And if it gets worse, If this were not a pain neuron, let's say this was in one of the muscles of your feet, so you know where your feet are in space, then that input region comes back to a dorsal ganglion. Then that very same neuron sends a process into the central nervous system and ascends the cord to the brainstem. So this literally goes from your feet to your brain. And not in me, but in some people, this could be 6 feet. And so these are extremely long axons. And again, emphasizes the point of axoplasmic transport, because all those proteins have to be made in the neuronal cell body, even for these sensory neurons. But now let's imagine that we now sever the cord. We talked a little bit about severing the cord yesterday, where we cut the cord completely through, but retained the reflex arc. But we're going to do this thing a little bit differently today. All we're going to do here is we're going to cut the cord right to the midline. Let's go to the upper panel and let me define this. Cutting the cord, I should say the spinal cord, to the midline. This has a name. It's called Brown. It's named after these neurologists, Brown-Séquard syndrome. This is simply a fancy way of saying a hemisection of the spinal cord. Now, I want to go through this not so much so you know what Brown-Séquard syndrome is, but I want to go through this because if you can follow the logic of Brown-Séquard syndrome, you have a really good understanding of how these pathways are carrying information, what information they're carrying, and what crosses over and what doesn't. So let's simply take the case where we have cut the cord here above the site where these primary sensory afferents enter the cord, but we only cut it halfway across. So now, let's now ask the question, does this person have an understanding of where their thigh is in space? So let's follow the proprioception pathway. Primary sensory afferent comes in. Primary sensory afferent stays on the same side, goes all the way to the brainstem. Then the second order synapse on the second order neuron, it crosses over, goes to the thalamus, and goes to the cerebral cortex. So yes, fine touch and proprioception gets through just fine. But let's take the other side. On the other side, now we're on the left side. We've cut the left side of the spinal cord. We now follow the pathway of the primary sensory afferent carrying information about proprioception or fine touch. We follow the axon, it comes into the cord, heads up, ascends the cord in the dorsal columns, but now we've cut it. We've cut the wire, so no information gets through. Meanwhile, although from the right side, this person doesn't know where their thigh is in space and has no fine touch in the region of the thigh. If you now poke them with something and cause pain, let's follow that pathway. We'll use the toe, but we could use the thigh. So you poke them with someone and cause pain or temperature, if you will. That information comes in, synapses almost immediately, crosses over the midline, and ascends the cord on the opposite side. So this person is going to still feel pain and temperature coming in from the right side because it crosses over and is not intercepted by the cut. So what gets through on this is pain, crude touch, but what's intercepted is fine touch and proprioception, which is the opposite over here. Over here, we find that our proprioception gets through just fine, but we no longer can feel any pain or temperature in this left leg. If you can walk your way through that, if you can practice walking through that and understand what finds its way to the cerebral cortex and what doesn't, you understand what modalities are being carried in these pathways, and you understand where information is crossing over and what can get through and what can't on those pathways. You have a complete understanding, pretty much, of the somatosensory system. So any questions to there? Yes, and then we'll come back, yeah.
How tough are these axons that go all the way from the foot up into the brain?
So the question is, how tough are these axons? And the answer is not as tough as we'd like. I mean, I don't know if you watched the game, but there was a football game last December where there was a linebacker from Pittsburgh Steelers who tackled someone midfield. And he hasn't had use of his leg since. He basically damaged the spinal cord, and it looks like he damaged it all the way across because it's not a hemisection. So these are really fragile. Now we protect them with our vertebral column. We protect all of the spinal cord is encased in bone, so that helps us some. But if you get the wrong shock on it, you get the wrong twist, you can damage these neurons.
But outside of that, like in the leg, like let's just say you had access to it, how hard would it be to cut it or?
So the question is, if we talk about the peripheral nervous system, these are relatively tougher because they're surrounded by a connective tissue sheath. And they appear to be pretty good at accepting a certain amount of stretch and torque. So we turn these things all the time. So torque and stretch and concussion seems to cause much greater damage to the central nervous system neurons than those guys in the periphery. What's more is that these guys will heal themselves. You can cut one of these axons, and if you're lucky, they'll regrow to their old sites. In the peripheral nervous system, you get pretty good regeneration, but not in the central nervous system. Then there was a question in the back.
Yeah, do all sensory inputs come in at the same location on the spinal column?
Do all sensory inputs come into the same site on the spinal column? And this is a really good point. I've simplified this to say that stuff coming in from the thigh is going to come into one particular dorsal root ganglion. But that really isn't true, because we have 31 pair of these dorsal root ganglia. And for instance, 4 through 6, I think, are carrying information in from your hands. And it'll be the lumbar region will be carrying information in from the legs. And I don't remember the numbers. That's all known. If you take an anatomy course, you'll learn all about that. But you're right. There are different primary sensory afferents coming from different places who will have their cell bodies in different dorsal root ganglia. And they will also then come into the cord, and they will maintain that relative body position all the way up through the system. And that will be an idea of somatotopy. And what we're going to look at is not so much the somatotopy all the way along the tracts, but we're going to emphasize the somatotopy once we get here in the cortices. Okay. Any other questions? Yes? Can you say that again, please? Okay, which sides would feel the pain? Well, let's follow. We've cut it here. And so now, if we pinch the toe or poke the thigh, that information is going to come in, synapse onto the second order neuron. It's going to cross over. We haven't intercepted that one, so it goes right up. But if we take the information from the left side about pain, then the second order neuron's been cut someplace up here, someplace between the lumbar region and the cervical region. We've cut it. Now that's going to intercept the second order neuron, so no information is going to get in to the subsequent synapses to get to the cortex. Okay? Yeah?
And all of that would be flip-flop, and heavy section coming in from the other.
So the question here is, okay, what happens if we leave this intact? And do the same thing on the other side. What a great exam question. And you're right, you're going to flip it just round. So what's going to happen here, if you cut this, then this second order neuron coming from what we've labeled as the right side is broken. But the information from the left side about fine touch and proprioception is broken. So but on the other side of the coin, pain gets through from the left side. So you just flip the whole story. Yes?
Is there much of a difference in the speed of information traveling in the spinal tract versus the dorsal?
Is there much difference in the speed traveling in the spinothalamic tract than in the dorsal column? Probably so. Because particularly proprioception, the proprioception primary sensory afferents are some of the most heavily myelinated neurons in the body. It's one of the reasons why the reflex arc is so quick. And we haven't talked much about it, but the reflex arc is pretty important to us. And we do this without thinking about it. And it's truly a reflex. We've all had the experience where we're walking along and we catch our toe on the sidewalk. Well, that reflex, that change in the stretch in the muscles of the leg, that's immediately transferred as a reflex, so that you'll then, if you've caught your right toe, you'll then transfer weight to the left side before you swing forward the right foot. Now, the swinging forward is all central, but the change in position comes from the stretch receptors, and that's a reflex, and that's spinal. And that's really fast. But to follow up on your question, many of these pain neurons, even sharp pain and heat, those are myelinated axons, but their conduction velocities in the neighborhood of 75 or 60 meters per second, rather than the top speeds of 110. So they're slower, but they're only about half as slow compared to the unmyelinated deep pain. So, and when we talk about pain, the initial pain when you stub your toe is coming through myelinated neurons. But then once you are over the initial pain and it's hurting long term, that deep throbbing pain, those are unmyelinated pain neurons. And they're following the same pathway. And they're going to end up, it'll be later getting to the somatosensory cortex, but they'll follow that same pathway. Anything else before we go to some slides?
I got one.
Yeah.
So the primary sensory apron synapse with the second order neuron in the dorsal root ganglion or at the thalamic relay nucleus?
Okay, important question, because the word was said here, synapses in the dorsal root ganglion. Now, the dorsal root ganglion is unusual. It's only neuronal cell bodies. It doesn't have much in the way of any synapses in it. It's just a pass-through. It's a collection point for the primary sensory afferent cell bodies during development. But it's simply an electrical pass-through for the signals. That's unusual because if we start getting into the sympathetic ganglia, then we have proper synapses. So what was the second part of your question?
So the synapse would then be at the thalamic relay nucleus.
So then the first synapse of this primary sensory afferent is onto the second order neuron. So 1 to 2.
Right.
And 2 for the spinothalamic tract occurs in the spinal cord. But 2 for the dorsal column system occurs in the brainstem nucleus.
Perfect.
Okay. 1, 2, 3 helps a lot. Anything else? Yes.
I can't remember exactly what it's called, but like the ghost limb pains, like it's an amputee.
Oh, phantom limb pain. Let me hold off on phantom limb pain. And when we get to the slides, we're going to run through a series of slides now. Stick your hand up again if I don't say something about it, because we can talk about phantom limb pain in terms mostly of what's going on in the central nervous system. Because there's some of that we understand from what's happening in the somatosensory regions and probably other parts of the brain. But let's look at this first. This is just to give you an initial image of the three-dimensional organization of the spinal column, the spinal cord rather. I like this image because I can't draw in 3 dimensions at all. But what it shows here, this is the dorsal or posterior region, here's the ventral region, and this is now showing the segmentation pattern along the spinal cord, showing the pairs of the dorsal root ganglia. It also shows how beyond the dorsal root ganglion, there's a fusion of the ventral root and the dorsal root to form the spinal nerve. And all the dorsal root ganglion, all of this is in the periphery. Then if we follow a process in from the dorsal root ganglion, they will then enter through the dorsal region. They'll go into the gray matter of the dorsal horn. Then in the ventral horn down here, there'll be cell bodies of lower motor neurons, and they'll send processes out on the same side through the ventral root to join the spinal nerve. And so this shows the organization of the white matter. It shows the organization of the gray matter. It shows the relative position of the dorsal and ventral horns, the relative position of the dorsal and ventral roots, as well as the spinal nerves. And it shows the segmentation pattern of these 3 segments. This is just about 10% of all the segments, since they're something in the neighborhood of about 31 segments in dorsal root ganglia. Now, the next slide is meant to show the distinction in the white matter. So the gray matter is shown here with a butterfly. Remember, whenever you see gray matter, recognize that that is neuronal cell bodies, it's input regions, and so it's gray matter. Everything outside the gray matter, the integrative regions, is now white matter. These are long-distance communication channels. But the long-distance communication channels also have regional specificity. And what I mean by that is there's some regions shown in blue that are going to be carrying ascending or sensory information. There'll be some regions shown in red that are carrying descending or motor information. Since we're talking about the sensory systems, let's follow through on the sensory. The one we've talked about here is the dorsal column system. So the sensory neuron, the primary sensory neuron, this primary sensory afferent, a cell body out here that's carrying information about proprioception and fine touch, will send a process in. One branch will go down to the ventral horn, fair enough. But the other branch is going to enter the dorsal columns and ascend the cord in the dorsal columns before forming synapses in the dorsal column nuclei. But if we followed another pathway, which if this neuronal cell body out here were for neurons carrying information about pain or temperature or pressure, that neuron would come into the central nervous system. It would enter the gray matter of the spinal cord right here in the dorsal horn. And almost immediately after entering the dorsal horn, it forms a synapse onto the second order neuron. Remember, all good second order neurons cross the midline. where the second-order neurons of the DCML or PCML cross in the brainstem. The second-order neuron for this pathway will extend a process from its cell body across the midline and enter this region down here called the spinothalamic tract. Now in this image it's called the ventral spinal or the lateral and ventral spinothalamic region. Turns out there's a lot of information coming through this tract. And if you take a neuroanatomy course, you'll see a number of different pieces of information that are being carried in this tract. All I want to talk about is the tract, which is the spinothalamic tract, where the neuronal cell body, the second-order neuron is located here, crosses over and ascends the cord now on the opposite side. Then let's follow it through in these images. Let's start with the proprioception and fine touch. This is just a line drawing of what we've drawn, what we've talked about. Here's the primary sensory afferent. Processes enters the gray matter, the one we talked about with the reflex arc, synapses directly onto a lower motor neuron. But the process we're talking about today is the one that ascends the cord in the dorsal columns. The output region of this neuron is now found in the dorsal column nuclei. In the dorsal column nuclei, this neuron synapses onto the second-order neuron. The second-order neuron is the one that crosses the midline. So it sends a process out from the dorsal column nucleus, crossing the midline and ascending into the thalamic relay nucleus. In the thalamic relay nucleus, number 2 synapses onto number 3, and number 3 now goes to the somatosensory cortex. So if we cut the cord on this side, we'll intercept this dorsal column system. That's in contrast to this guy, where here's our primary sensory afferent, enters the dorsal horn, synapses onto the second-order neuron, crosses over the midline, and now ascends the cord in the spinothalamic tract. So now this second-order neuron goes all the way from the gray matter of the spinal cord all the way up to the thalamus, and then synapses onto the third-order neuron here in the thalamus, and its output regions of the third-order neuron are now in the somatosensory cortex. But again, 1, 2, 3, 2 always crosses over. So if you keep track of that, you can think about these things fairly easily. And you can see, too, from the way this crosses over, if we had a hemisection of the cord, this information gets through from this side just fine. So now, where's it going? This is an image of the brain, and I want to use it simply to introduce the sites where we're going to have the axon terminals of those third-order neurons. So if we look at this, it's as though I'm looking at this far wall, and we've removed the left-hand side of my skull, and you're looking down onto my brain. And so what we're looking at now is this region here. What I want to emphasize is this interface between the pink region and the blue region. This interface here is called the central sulcus, and it's a dividing point. It's a really important landmark. And if we would take the skulls off of anyone in this room, we would find this same pattern. And the way this was discovered was actually in surgeries. And there was a fellow named Wilder Penfield in the early part of the 1950s. In the early part of the 1950s, Wilder Penfield was doing surgeries on individuals who had intractable epilepsy. And he recognized that if he could find the site in the brain where the epileptic seizures were beginning, the point called the kindling point, if he could go in and excise or take out that tiny part of the brain, he could in many cases rescue people and their lives from these epileptic seizures. But he also recognized that if they cut out too much of the brain, he could then compromise really, really important aspects of function. So being a very careful neurosurgeon and an even more careful neurobiologist, what he would do with these individuals is he would anesthetize the scalp. He would then pull back the scalp and then take a bone saw, cut through the skull, pop off the skull, and look down at the brain. And in the early days, he literally did this with his finger. He literally would start poking around in the brain. And when he would poke in this region here, known as the postcentral gyrus, which is part of the parietal lobe, he'd poke in some region here, and they'd say, "Oh, I feel that in my face," or "Oh, I feel that in my hand." Whenever he would poke in a particular spot, they would always say, "That's my face." In another place, they would say, "That's my hand." And when he would poke at the precentral gyrus, he would then get movement. sometimes in the hand, sometimes in the face, depending on where he touched the surface of the brain. Now, in the final minute, let me show you this image. Again, facing this wall. Here's the precentral gyrus, the procentral gyrus in blue. The postcentral gyrus here now is the somatosensory cortex. This is the map of the body plan on the somatosensory cortex. So when Walter Penfield poked here, the person said, I feel it in my face. When he poked here, he felt it in the hand. He or she felt it in the hand. Now, what I want you to remember from this is that the anatomical size of the unit of the body is disproportionately covered by the region of the somatosensory cortex. That's best shown here in this three-dimensional model. This shows the disproportionate innervation from the hands and the lips. I mean, Mick Jagger doesn't have lips like that. And with that, I'll let you go.